Assalamu alaikum student. Welcome to my virtual classroom. Today I like to discuss on anharmonic oscillator. Last lecture I discussed what is harmonic oscillator or harmonic oscillator, what is its potential energy and energy line, then reflection rule and spectrum. Today same topics but for anharmonic oscillator we will consider. So let's see. For harmonic case, harmonic oscillator, energy expression was mu plus half omega bar OST in per centimeter. And the energy line diagram was like this. And selection rule was that transition takes place between two adjacent line, that is delta mu was plus minus 1. So for anharmonic case, the energy expression will also be changed and selection rule will also be changed. For anharmonic oscillator, anharmonic oscillator So first of all, what is harmonic oscillator and what is anharmonic oscillator? You see in this figure, whatever the value of mu, for any value of mu is equal to maybe infinity, no doubt. But in case of anharmonic oscillator, with increasing mu, and mu, it has some maximum value. You cannot have infinity value. That is, at certain values of mu, the bond of the molecule will dissociate. That means, suppose this is a diatomic molecule, so it can vibrate about its equilibrium position with some extension and compression. Suppose this is normal vibration, but if the vibration is extended to this mass, at this position the bond will break. So when bond undergo rupture, undergo breaking, then the molecule are no longer harmonic, and when not harmonic, then Hooke's law cannot be applied. So that's why one scientist named Morse, M-O-R-S-E, Morse, scientist Morse, he modified the energy and force expression for anharmonic cases. For the harmonic case, we discussed that this energy is equal to half K R minus R equilibrium square, and energy was mu plus half into OS bar. But in case of this is the harmonic case, this is the expression of the harmonic, but anharmonic, that is Morse consideration. According to Morse consideration, energy of molecule that was given by the equilibrium 1 minus exponential A into R equilibrium minus R second bracket third bracket whole square. So this is an empirical equation. According to this equation, when we consider harmonic, force vary according to Hooke's law, But in case of anharmonic case, the energy, sorry, the force does not vary according to Hooke's law. So scientists empirically drive an equation, and the force vary according to this line, where D equilibrium, the bond dissociation energy, A is another constant. A is constant, depends on molecule, and R equilibrium and R, these are as same as before, same as harmonic case. Therefore, according to this equation or Morse equation, the variation of energy, potential energy of molecule will be like this. If you consider the dot line is the harmonic case, which is the perfect parabola. But in case of Morse consideration, this is something like the, that means as a result of compression, the molecular energy increased sharply, but extension, after a certain V value, the energy remains same. That means this zone represents the bond breaking zone. So energy does not increase. It's a bond breaking. So that's why we can consider, suppose this one, this distance, which is known as the equilibrium, and here say zero level and the upper level. As we go upper, the line become very close to each other, and at a certain value, bond undergo rupture. Suppose this one undergo rupture. So according to this one is the exact bond dissociation energy, which is called D naught. And this mass energy from lower to top, bond dissociation, and zero level to top is known as bond dissociation energy, and this is equilibrium energy. Equilibrium bond dissociation energy. Types of energy there. So you see, this curve is called Morse curve. MORSECQRV. Morse curve. In honor of energy of the molecule, considering anharmonic, the variation is like this: the solid line. Compression case, energy increase sharply, but extension case, increase, but after certain value it does not increase. That means bond undergo rupture or breaking. So so in case of anharmonic oscillator, the energy obviously comes from the solution of Schrödinger equation. Similarly, for the harmonic case, Schrödinger equation. And in this case, if anharmonic case, if we put this value in Schrödinger equation and solve the equation for vibrational energy, we obtain the energy is given by mu is equal to mu plus half mu E bar. Note it, mu E bar, and minus mu plus half whole square mu bar, another term x. So for anharmonic case, that is for harmonic case, we have the expression OSC like this. So almost similar, but there is a correction part. This part is almost harmonic case, exactly harmonic. But in case of harmonic, anharmonic by anharmonicity, harmonic energy minus some correction energy. So the energy becomes energy for an harmonic molecule. So here we have two terms newly introduced. One is the mu E bar, another is the X E. So mu E bar, this is obviously oscillation frequency, but it's called equilibrium oscillation frequency. Equilibrium oscillation frequency, and X is the anharmonicity constant. Anharmonicity constant. So X is always positive. Its value is always positive. It cannot have value 0 or negative. Xc and harmonicity constant is always positive and very small, in fact, very small. Very small means Xp more or less, obviously you can put plus, and it is 0.01 like this and around 0.01. So very small positive value is for anharmonic constant. So today you see, in case of anharmonic oscillator, we obtain the energy by this expression, which is slightly different than this harmonic case, because in case of harmonic we do not have a correction term, but here we have some correction term, and due to this correction the energy levels are not equally spaced. In case of harmonic oscillator, energy levels are equally spaced, but in this case, anharmonic case, as we go up, that is increasing the value of mu, that is vibrational quantum number, the energy levels get more crowded. As we go up, the energy level gets more crowded. This is the difference between the harmonic and anharmonic case. Here, we have to explain what does equilibrium oscillation frequency mean. So for that, we little bit modify this equation. You see, this is common part, mu plus half into omega E bar, and we have also omega E bar and mu plus half. So if we take common this part, omega E bar mu plus half, so what we left here, this part we have 1, and this part 1 mu plus half gone here. So another part is remaining, which is this, and mu E bar also common taken, so we have only 8. So this is little bit modified form. And if we consider the harmonic case, we can write it, we can also write it like this. So suppose this is on equation 1 and this is on equation 2. So left hand side of equation 1 and 2 are same, therefore right hand side must be same. Right hand side also must be same. So that is equation 1 and 2. From equation 1 and equation 2, we have left side equal, so right hand side will also be equal. Right hand side is also equal, that is 1 omega E bar 1 minus mu plus half times x. The same. Oh, sorry, one common part also here. Mu plus half common, and the other part is this one. So you see, both sides we have this part, so we can cancel this one. That is, if we cancel this one and cancel this one, and write omega E bar here. So suppose this is equation 3. So what does this equation 3 signify? Student closely look. This is also frequency. This is also frequency. Frequency of oscillation for harmonic case and frequency of equilibrium oscillation for anharmonic case. So anharmonic oscillator behaves like harmonic oscillator. Only the frequency of oscillation decrease because we have some minus correction, decrease with increasing the value of mu. So these equations signify that anharmonic oscillator behaves like harmonic oscillator, but only slight decrease of oscillation frequency with increasing the vibrational quantum number or mu. So this is one significance. And here, if we consider, let us consider a hypothetical energy state corresponding to mu is equal to minus half. Student, remember that mu it can have value 0, 1, 2, 3, etc. But here we are considering mu is equal to minus half. That's why we call the hypothetical energy level. Because mu is equal to minus half, in practice there's no such energy level. No such energy level that corresponds to mu is equal to minus half. But hypothetically we can consider such an energy level where mu is equal to minus half. Why we need it? Because you see, if we put mu is equal to minus half here, what will happen? Therefore, so OSC, oscillation frequency, you see mu e bar 1 minus, here we put minus half, and we have plus half, and we have XC. So this part is 0. So approximately oscillation frequency of harmonic oscillator is equal to oscillation frequency of anharmonic oscillator. So therefore, omega E bar is represent a oscillation, of course, frequency, oscillation frequency, okay? Oscillation frequency corresponding to a hypothetical level which is mu is equal to minus half. That means under that state, the molecule has zero energy, and it zero energy, but we can consider that suppose this is mu. So this energy is not zero, but we can consider a lower level, this part, here we have zero energy. So mu is equal to minus half corresponds to this energy, mu is equal to 0, this is non-zero corresponds to this. So molecule at equilibrium with the 0 point and vibrate slightly, that frequency is known as mu E bar. So that's why mu E bar is known as equilibrium oscillation frequency. Okay. So this is how we can define equilibrium oscillation frequency. Sometimes we set question for examination purpose. What does equilibrium oscillation frequency means? Then we have to write all these things. So now let us consider, as we have energy expression, so obviously we have origin of a spectrum, obviously. So this is our energy. This is not exactly omega E bar and omega E bar X bar. So this is energy of, this is the energy of oscillation, energy of an harmonic oscillator, and the energy level diagram is given by Morse card. Maybe right hand side is not necessary. You can plot it like this. So we have this part, and this part. Okay. So this is energy, this is R, and this is mu is equal to 0, 1, 2, 3, and 4 level. I have shown here. So according to this energy level, the Morse curve is this. But now the question, how we will get a spectrum? So spectrum means we have to make some transition. So in case of harmonic case, you can recall harmonic case, the selection rule was plus minus 1. So transition between two any adjacent level was permitted and only one spectrum was obtained. But in this case, selection rule is plus minus 1 obviously, but it can be plus minus 2, it can be plus minus 3, etc. So, in case of an harmonic oscillator, selection rule for an harmonic case is mu is equal to plus minus 1, plus minus 2, plus minus 3, and so on. So, student, you see the problem. Now, mu plus minus mu, delta mu is equal to plus minus 1. That means from 0 level to 1 level, okay. Plus minus 2 means 0 level to 2 level, okay. Plus minus 3, that means 0 level to 3 level. So it can be plus minus 4, plus minus 5, plus minus 6. So infinity possibility. But in fact, possible, but intensity for plus minus 4, plus minus 5 are so low and so less probable that instrument cannot detect those signals. So basically, we can consider these three values: plus minus 1, plus minus 2, and plus minus 3. Upper values, that is plus minus 4, plus minus 5, these are not under consideration because the spectrum become very, very low intense because of the low probability of those transitions. So we have to consider these three transitions. So according to the value of plus minus 1, plus minus 2, plus minus 3, we can name this transition or absorption band. So let us try. In case of an harmonic oscillator by an harmonic molecule, selection rule is this. And here we have to consider one fact, that is, in case of rotational spectrum, you can recall the energy population slowly increase and then decrease. That's why the spectrum also in intensity increase and decrease. But in this case, we have to first consider how many molecules residing at 0 level, 1 level, and 2 level. Okay, let us see. Suppose number of molecules residing mu is equal to 1 level and number of molecules residing in the 0 level. There is 0 point energy level a number of molecule and 1 level a number of molecule. That is this level and this. If we take the ratio, we can approximately say, oh, okay, number one energy level contain this mass molecule. So first of all, let us consider this ratio, 0 level and 1 level. So, and if we consider the energy gap between these two levels, suppose this is 10 to the power 3, that is 1000%. Energy level separation between 0 and 1 level, say approximately 10 to the power 3, that is 1000%. Yeah? So energy expression is exponential by e to the power. I will make this calculation also for rotational spectrum. Same thing. We have two CAs and energy in per centimeter. Energy in per centimeter times CAs. So it becomes energy in joule divided by Boltzmann constant times T. I hope students you can recall this one. Recall this one from my lecture on rotational spectroscopy. Now put the values. E to the power minus C is the light velocity, so we consider it 10 to the power 10 centimeter per second, and this value, in fact, this is delta E, and delta E means 0 and the gap, we have considered this gap, this is not exactly mu. There is separation, the energy gap between these two levels, and energy gap between these two levels is given by 10 to the power 3 per centimeter, and value of h is equal to 6 to 6, 10 to the power minus 34 joule second, divided by KT. K is the Boltzmann constant, 1.8 10 to the power minus 23 joule per Kelvin, and at room temperature around say 300 Kelvin. So if you calculate this value, you will get the value 0.008. What does this mean? Student, this means this ratio is approximately 0.08 means only around 1%, even less than 1%. So this ratio is 1%. So number of molecule in one level divided by number of molecule in zero level is equal to 1%. That means 100 molecule zero level and only one molecule is in the mu1 level. So we can consider mostly the molecule occupy the zero level. So we can, what is the conclusion? So the molecules of molecules mostly occupy level. So if we consider N2 N naught, then N1 N0 is equal to 1%. So N2 N naught, the gap will be greater. So this value will be also very, very low. So we can consider the upper transition, that is molecules are not available in 2, 3, 4. That means 0 level 100 molecules, 1 level only 1 molecule, and 2, 3, 4 levels are vacant. Suppose at room temperature these are vacant. So plus minus 1, therefore 2 to 3, 3 to 4 possible, but there is no molecule. So we cannot have the spectrum. So this calculation means, although according to selection rule, we have lot of possibilities of transition, but according to population, we see that only the ground 0 point level, that is mu equal to 0, all the molecule reside at mu is equal to 0 now. So from 0 to 1, 0 to 2, 0 to 3 transition can take place. Even 0 to 4 can also take place, 0 to 5, but those transitions are very less probable. That's why these are the transitions. Graphically, we can say from 0 to 1 or 0 to 2, another is the 0 to 3. So these are the basic transitions. So what are the transitions? Transitions are, suppose E is equal to 0 to epsilon, mu is equal to 1. This transition is called the fundamental absorption. Fundamental absorption band. So what is fundamental absorption band? If transition takes place from 0 level to 1 level, that mu is equal to 0 to mu is equal to 1, then the absorption band we obtain is known as fundamental absorption band. Fundamental means this absorption band appears most intense, and other bands intensity slowly decreases. So another transition, this is one transition according to plus minus 1, plus minus 2, that is mu is equal to 0 level 2, mu is equal to energy level 2, that is second one. So this is another transition, and this transition has also a name. That name is the first overtone, which we call first over tone, fast over. This is another band. We can have another transition. For this case, we consider the plus minus 2. And for this case, delta mu is equal to plus minus 1. So we have another plus minus 3. That one is the from mu equal to 0 level, transition to mu equal to 3 level. That one called second overtone. Second overtone. In case of second overtone, we consider mu equal to plus minus 3. So, student, you see fundamental absorption, first overtone and second overtone, and how to divide first overtone. Sorry, fundamental absorption, first overtone and second overtone. I already defined here. If the transition from 0 to 1, that is fundamental. If the transition from 0 to 2, known as first overtone. If the transition takes place from 0 to 3, known as second overtone. And in case of fundamental absorption, delta mu equal to plus minus 1, first overtone, delta mu equal to plus minus 2, and second overtone, delta mu equal to plus minus 3. Now you have to calculate the absorption wave number or absorption frequency of all these three transitions. Okay, let's start with fundamental one. So here all these things. Here all these things. Calculate now. This is find out expression. Find out expressions for one is the fundamental absorption band, fundamental absorption band. Two is the first overtone, and third and the last case is the second overtone. Okay. So for finding out expression for first overtone is expression for etc. for wavelength or wave number for 1, 2, and 3. Find out expression for wave number for 3 case fundamental. Second is the first overtone and third is the second one. So we have to have the energy expression first. So we again recall this equation. Energy of an harmonic oscillator, which is obviously this. So in case of fundamental absorption, we have to replace mu with 1 minus with 0. That means mu is equal to 1 minus mu is equal to 0. We have to put this value. So first of all, we have to put mu is equal to 1 and 1 minus 0, 0. Then we get find out the gap, and therefore when absorption is mu is equal to 1 minus this expression, we have to put mu is equal to 0 minus mu is equal to mu is equal to 1 minus mu is equal to 0. So put the values. Mu is equal to 1 plus half omega e bar minus mu is equal to 1 half whole square omega e xt. So this is the first case, that is energy for the 1 level minus energy for the 0 level. So energy for 0 level is mu is equal to 0. So mu is equal to 0 means 0 plus half omega e bar minus mu is equal to 0 half whole square omega e bar x. So if we evaluate these things, let us see 2 times 1, 2 plus 1 is 3, 3 by 2. So we obtain 3 by 2 omega e minus 3 by 2 whole square. So 9 divided by 4 omega e x. Here 0 plus half equal to half. So we have minus sign, minus half omega e bar divided by 2. And this minus also plus. You see 0 plus half equal to half whole square of half, that is 1 by 4. 1 by 4 omega e x. So we have two types of terms. One is the omega e, another is the omega e x, omega e x. So 3 by 2 minus half. What is that? 3 by 2 means 1.5. Means 0.5. So simply omega e bar. So this 9 by 4 minus plus 1 by 4. That means 1 by 4 minus 9 by 4. So it will be minus 8 by 4. 8 by 4 means 2. So we can write 2 omega e bar x. So from here we can take common omega e bar common. So 1 minus 2 x e. So this is the, obviously this is in per centimeter. So student, you see the fundamental absorption band appears at this percent, appears at this wave number. What is that? Omega e bar times 1 minus 2x. For approximation, this can be write approximately omega e bar. Why? 1 minus 2x. 2x is very low. X is very low. That is 0.01. So 1 minus 0.02. 1 minus 0.02 means close to 1. That's why we can consider the absorption band, that is fundamental absorption band, appears at approximately omega e bar. So similarly, you can consider the first order. In case of first order, we have to maybe delete up to this. And in case of first order, obviously energy gap 2 level to 0. So student, this time you have to put in this equation mu is equal to 2, and another expression mu is equal to 0, mu is equal to 0. So we write mu is equal to 2 plus half whole square omega e x e. So plus half whole square omega e bar xt.
এ স্যার কি নাই?
স্যারের মনে কারেন্ট চলে গেছে, এই জন্য নেট চলে গেছে, এরকম কিছু একটা হবে।
কি অবস্থা বন্ধু?
এই তো, তুই তো হোস্ট এখন।
হ্যাঁ আমি ক্লাস নেই।
খেয়াল হোক, খেয়াল বাকিটুকু কমপ্লিট কর।
আমি তো আগের গুলাই বুঝছি না, পরের গুলো কি বুঝাম?
পরের ক্যালকুলেশনটা করে
আমার নেটে ডিস্টার্ব করে।
মাহফুজ তো নাই স্যার।
মাহফুজের বোধহয় কারেন্ট চলে গেছে।
আমিও তো ডিসকানেক্ট হয়ে গেছিলাম রে বাবা। কতদূর পাইছিল এই যে ফান্ডামেন্টাল অ্যাবজর্পশন ব্যান্ডের ওয়েভলেন্থ বের করা পর্যন্ত পাইছিলা?
জি স্যার,
হ্যাঁ
জি স্যার, এইটুকু পর্যন্ত লিখছিলাম।
হ্যাঁ, এই যে উপরে কিন্তু আমার যে ডিসকানেক্ট হয়ে গেছে, আবার যে ভিডিও যেটুকু রেকর্ড হয়েছে ওইটুকু কনভার্ট হইতেছে। তাহলে আজকে বাদ দে, কি কও? হ্যালো,
কি আছে স্যার?
ঠিক আছে স্যার,
ওই ধরো যেটুকু হয়েছে ওইটুকু, কারণ ভিডিওটা নষ্ট হয়ে যাবে যেটুকু হয়েছে আমার।
ঠিক আছে স্যার।
ঠিক আছে স্যার।
আচ্ছা, তাহলে তোমরা একটু লিড করো।